So in this chapter, we'll be talking about atoms. So in the last chapter, we left off on classifying matter, talking about the properties of matter. And in this chapter, we actually dig into what makes up that matter, so atoms and compounds. So I want you to imagine that we have a piece of lead and that we are cutting it into really small pieces. Could we keep going on forever in terms of cutting it into tiny little pieces? The answer is no. So eventually we would get down to the atoms, and those are actually carbon atoms. And atoms are what make up all matter. And if we want to understand matter, we need to understand atoms. So obviously, we did not discover atoms right away. There's a very long history to how atoms were discovered and how all the details of what make up an atom were discovered. So some very, very early ideas about atoms started with Leucippus and Democritus, who were like philosophers. But they actually were pretty spot on, and they argued that all matter was composed of small finite particles. And then Aristotle came along. I'm sure you guys have heard of him. And he proposed that matter was made up of 4 elements like earth, wind, fire, whatever those are. And he thought that if we took that graphite, let's say again, that we would be able to cut it up infinitely. So he thought that matter was infinitely divisible. And this was actually accepted for like 2,000 years until more scientists ended up disproving this. So the first of those scientists is French chemist Antoine Lavoisier. He formulated the law of conservation of mass, which is essentially the idea that when you start off with a certain amount of matter, and then a chemical reaction occurs, you're going to end up with the same amount of matter after. It doesn't matter what type of chemical reaction occurs, you end up having the same amount at the end. So, for example, you start off with 7.7 grams of sodium. You react with 11.9 grams of chlorine gas. Total, you have 19.6. Once you react this, you'll end up getting 19.6 grams of table salt, sodium chloride. So you will always have the mass of reactants equal to the mass of the products. So next we have the law of definite proportions, which was postulated by another French chemist, Joseph Proust. He summarized that when you have more than one sample, whatever the sample may be, of one type of compound, regardless of where it came from, how it was prepared, you will have the same proportion of the elements within it in whatever sample it may be. So here you have 3 samples. You have sample A, B, and C. Each of these, who knows where they came from? But you end up having a certain amount of carbon and hydrogen in each of them, right? When you divide these out, you get the same ratio for all of these. And this is of isooctane if you wanted to know the formula. And just to show you the ratio in a different manner, if you're curious, it's 5.33 to 1. So 5.33 grams of carbon to 1 gram of hydrogen, always for any type of sample of isooctane. And this is the law of definite proportions. So before I get started on explaining the law of multiple proportions, I want to point out the major thing that I think will help you differentiate between the definite proportion law and multiple proportion law. For definite proportion, you have one compound. So for example, on the previous slide, we had isooctane, and we had 3 different samples of it. So for definite, it's one type of compound and multiple samples of it. For multiple proportion law, it's several different compounds, but they have the same types of atoms within them. So we're going to go ahead and look at an example right now. So for the law of multiple proportions, this states that when we have 2 elements, let's say we're going to call them A and B, when they form 2 different compounds, the masses of element B that combine with 1 gram of A can be expressed as a ratio of small whole numbers. So for example, in this case, we have carbon dioxide, and we can relate this to that general term as AB2, right? For carbon monoxide, we can relate this as AB1, right? They both have carbon and oxygen, they just have different numbers of oxygen in them. Now, when we divide the masses of element B, right? That's what the law states. So I have B2 on top of B1. We end up getting a ratio of 2. And when you actually divide these masses out that you get experimentally, you get that ratio. So this is what that law states, that you will have a ratio of small whole numbers between two different compounds that have the same types of elements. So from these laws, John Dalton established the atomic theory, and essentially what this theory states is that atoms are what compose elements. Elements have certain properties to them that make them unique. They form compounds, and finally, atoms don't change into other atoms in chemical reactions. That's something completely different called nuclear chemistry, when atoms start decaying and turning into other elements, and we don't talk about that in this class. That's in Chem 2. So by this point in time, scientists were pretty convinced that atoms indeed existed, but they didn't know if there were subatomic particles, meaning can we break down the atom further? Is it made up of its own building blocks? And the first of the three major experiments that led to the discovery of these little building blocks within an atom was the discovery of the electron by J.J. Thomson and his cathode ray tube. So what he did was he had a cathode ray tube shown here. This tube was under vacuum, and he was passing a beam of electrons through the tube. The beam was passed through two plates, so you had a positively and a negatively charged plate. What ended up happening was that this beam repelled from the negative side and it was attracted to the positive side. So you can see here it went closer to the positive. So what he concluded from this was that electrons must have a negative charge since they were attracted to the positive. They are very light, and he ended up actually calculating the charge to mass ratio from this. So the next experiment was Robert Millikan's oil drop experiment, and this experiment helped us understand the charge of the electron. So what was happening was that he had oil being atomized and sprayed into tiny little droplets into this little chamber, and he then hit those droplets with an X-ray in order to produce a charge on them. These little drops that had charges on them passed through these two plates, and then a different strength of field was varied in order to basically produce a lot of measurements of different charges. From there, he ended up concluding what the charge of the electron was, like an actual value to it, and he was also able to calculate the mass using what he measured, the charge, and the mass to charge ratio that Thomson had measured. So you can see here the little dimensional analysis setup that he used to figure out what the actual mass of an electron was. So by this point in time, scientists had proposed several atomic models. The first of these is the plum pudding model, which was proposed by Thomson. And he thought that we had positively charged matter, and within it, embedded, we had electrons. And it was named plum pudding after this dessert from, I think, the United Kingdom. And all I honestly can think of whenever I see this is SpongeBob's parents. That's exactly what the plum pudding model looks like to me. So hopefully that helps you remember that. And the second model at this point in time was the Hontaro Nagaoka model. This was like essentially the planet Saturn, where you had a positively charged matter in the center and then a ring of electrons around it. So the third and final experiment we're going to talk about is Ernest Rutherford's gold foil experiment, which led to the discovery of the proton. So what happened was he was shooting a beam of alpha particles, which all you have to know about these is that they're positively charged. He was shooting these at a piece of gold foil. Now behind this gold foil, he had a detector. What ended up happening was a lot of these alpha particles ended up being detected directly behind the gold foil. What this meant was that most of these particles were just passing straight through the foil, which tells you that the solid gold was actually a lot of empty space, which we will talk about later. But the important finding from this was that some of these were deflected. So every once in a while, out of all those particles being shot, some of these were hitting the complete opposite side of the detector. Now, the important part of what those deflections tell you is that we know those particles were positive, right? The ones that he was shooting through the gold foil. in order for them to be deflected, that must mean that they have to have encountered something else that was positive. So the alpha particles must have encountered another positive charge. So the two major things that he concluded from his experiment was that volume occupied by atoms is mostly empty space because a lot of those just pass straight through the foil. And secondly, a small positively charged body, which we later called the nucleus, is at the center of each atom. So he did more experiments and he realized that the positively charged subatomic particle in the nucleus is actually a building block of the elements, which we now call the protons. So Ernest Rutherford actually worked under Thomson, and when he was doing his gold foil experiment, he was originally trying to provide data to support Thomson's model. And based off of Thomson's model, the plum pudding model, what you should end up seeing is that the alpha particles just pass right through all of the matter, and since all the matter is positively charged, they should just pass right through essentially. That's the prediction for that model. But what Rutherford, like we observed, actually found was that there were deflections, and these deflections showed that there was a nucleus with some positively charged particles in there. So I'm sure that Thomson was pretty confused whenever Rutherford made his own model, but this ended up being Rutherford's nuclear theory. So even though Rutherford's model made a lot of progress in terms of what scientists knew at the time about atoms, scientists knew that it was incomplete. Now, it was incomplete because at that point in time, they were able to measure masses of atoms, and they knew that protons and electrons existed. When they would measure the masses of the atoms, they would account for all the protons, and it would always end up being that they had some amount of mass unaccounted for in terms of protons. So there was a mass, they would count the protons, and then they would have mass left over. What was making up this leftover mass? James Chadwick, who was a British scientist, demonstrated that this unaccounted mass was due to neutrons. And neutrons are particles that have no electrical charge, and they have a mass that is similar to a proton's mass. So if you hadn't known what you know now about the gold foil experiment, if I told you that atoms are mostly empty space, what would you think? Most people would say, no, how can atoms be empty space if I'm a solid, this table's a solid, my laptop's a solid? It makes no sense, right? But whenever we scale how big the nucleus is compared to an entire atom, if an atom was the size of a football stadium, so imagine that, the nucleus would be the size of a blueberry in the very center of it. So that's how much empty space there is between the nucleus and the entire atom, so all the electrons in the electron cloud. So when you actually look at the dimensions, matter is mostly empty space. Now, you're probably thinking, okay, if it's empty space, then why are we solid, right? Why is my human body solid? And this is because of the variation in its density. It's so small that we can't see it or feel it. So an analogy that can help you understand this is imagine that you are looking at scaffolding, like to build some sort of structure. It's mostly empty space whenever you zoom in on it, right? But if you looked at it from bird's eye view in an airplane, it would look like a complete solid. So it's very similar with matter. It's a very similar situation where if you look macroscopically, it's a solid, but if you look closer, it's actually a lot of empty space. So to summarize what all of those experiments demonstrated about atoms, we know that electrons are located outside of the nucleus, and within the very center of the atom, we have the nucleus, which is composed of protons and neutrons. Both the electron and proton have charges to them. Electron, you can think of it, they have a -1 charge, and the proton has a +1 charge. We don't actually use the value in coulombs, which is just a measurement of charge. We just look at it like units. Now, we know the masses, and we are going to be talking about the masses of atoms in a unit called AMU. AMUs are essentially kind of like an arbitrary unit defined using the mass of carbon-12, which is the most abundant isotope of carbon. We defined it as 12, and then we divided it by 12 since it was 12. It was 6 protons and 6 neutrons. And then what you get is that 1 AMU. So it's kind of like an arbitrary measurement, but don't really worry about that too much. It's pretty similar to 1 gram. And we'll talk about that later, grams versus AMUs. So elements are defined by the number of protons. This is very important for you to understand. I'm going to keep on reminding you about this. Elements are defined by the number of protons. If the number of proton changes of an atom, it is not the same element anymore. So, for example, any atom with 6 protons is carbon. If it has 7 protons, it's not carbon anymore. Any atom with 8 protons is oxygen. If it has 9 or 7 protons, it's not oxygen, it's a different element. And we denote this with the capital letter Z. And we know that what contributes to the mass of an atom is not only the protons, it's the neutrons as well. And that makes up a number called the mass number. So for the entire mass of the atom, we denote it with the letter A. It's the total number of protons and neutrons. Now, in terms of electrons, since most atoms are electrically neutral, we assume that the number of electrons is equal to the number of protons. So in other words, it's also equal to the atomic number. So from all of these numbers and denotations, we can calculate several things. So we know the atomic number is equal to the number of protons. We know the mass number equals protons and neutrons in the nucleus. And because of that, we can use both of these numbers to subtract and get the number of neutrons. So whenever we write chemical symbols, we only capitalize the first letter of an element symbol if it has more than one letter. So for example, cobalt, it's capital C, little o, not big C, big O, which is carbon and oxygen. That's something completely different. Indium is shown as I, capital I, and then lowercase n. It's not capital I, capital N, which is iodine and nitrogen. Whenever we look at the chemical symbols that have mass number and atomic number written on them, this is how it will be set up. So you will have the chemical symbol, and then you'll have the atomic number Z. Down here at the bottom, it'll always be the smaller number, and then the mass number will always be the bigger number up here at the top. Another common notation, especially for isotopes, is you will have the chemical symbol followed by the mass number. So isotopes are essentially different versions of the same type of element or atom, but the difference between them is that you have differing numbers of neutrons. So for example, all neons have to have 10 protons. If it doesn't have 10 protons, it's not neon, it's something else. But the difference between some of these neon atoms is that they may have 10, they may have 11 or 12 neutrons. All of these are stable, they exist, but they all have different masses. And what they're called is isotopes of each other. They're isotopes of neon. So atoms with the same number of protons but different number of neutrons are called isotopes. And then this is just showing you different representations. So chemical symbol with the mass number and the atomic number here, mass, atomic number. This is the chemical symbol and the mass number, and so on. So just to recap, we've talked about the number of protons and how that defines elements. When you change the number of protons, you get a different element. We've talked about what happens when you change the number of neutrons. You get an isotope of that same type of element, another isotope. Now, what happens when you change the number of electrons? You get something called an ion. This happens when atoms develop charges where they are undergoing some sort of chemical change and they either lose or gain electrons. They end up becoming charged particles, and specifically they're called either cations or anions. Cations are positive, I hope that helps you remember that, and anions are negatively charged ions. Now here we have an example. Here we have a neutral sodium atom. This sodium has 11 protons, 12 neutrons in the nucleus, and then it has 11 electrons. Now remember what we talked about, how protons have a positive 1 unit charge and electrons have a negative 1 unit charge. When we add these up, we end up getting 0. Here we have a sodium with 11 protons, 12 neutrons in the nucleus, and then we have 10 electrons. When we add this up, we end up getting a positive 1 left over. So that's why this is a sodium cation compared to this electrically neutral sodium atom. So now we are going to work on a problem where we have to determine the number of subatomic particles. So in this first example, we are looking at zinc, and they gave us a mass number of 65, and they told us it contains 31 electrons. How many protons, neutrons, and electrons does it have, and what is its charge? Now, to save us time, what I did was I went to my periodic table and I looked at what the atomic number of both of these elements was. So the atomic number is Z, and it tells us the number of protons. So far what we have is our number of protons. So I'm just going to write P for protons. We have 30. So we have one thing checked off so far. Now they gave us our mass number. Mass number is A, so that means that this is 65. Now to get our number of neutrons, we have to subtract our Z from 65. So that is going to be 65 minus 30. So this is the mass number minus the atomic number. That gives us 35. So that tells us we have 35 neutrons. Finally, the problem actually tells us we have 31 electrons, so we can go ahead and write that in. And then the last question is asking what is its charge. So we know that we have 30 protons, we have 31 electrons. We have one extra electron compared to protons. That means that you're going to have a -1 charge because we know electrons are negatively charged. So this will have a -1 charge. Next, we're looking at osmium. So I went to the periodic table and I looked at what the atomic number for osmium was, and I wrote it down right here, which is 76. And it actually told me, so I didn't have to go to the periodic table, but the problem also tells me I have 114 neutrons. So we know that we have 76 protons because the atomic number is 76, and the problem told us we have 114 neutrons. Oops. And then what we need to figure out is how many electrons it has. So whenever a problem does not tell you how many electrons an atom has, and it also does not tell you, okay, it has a -2 charge. If it doesn't say anything, that means you can assume that the number of electrons is equal to the number of protons. So in this case, we would have 76 electrons because you always assume that atoms start off electrically neutral. So in this case, it would not have a charge. It would be neutral. And for our A, just to fill this in, our mass number would be our protons plus our neutrons. So when we add that up, we end up getting 190. And we didn't have to do this part because the problem already told us how many neutrons we had. So now that you know that mass number of an element is equal to the protons and neutrons, would you sit here and wonder, why does this have a decimal point? Like, there's no half of a neutron or half of a proton, so how can it have 0.45? And that is because the atomic mass that you see on the periodic table are usually the average atomic mass, which is weighted according to the natural abundance of each isotope. And essentially how they calculate it is through this equation, which we are going to practice on the next slide. So here we have a problem stating naturally occurring chlorine consists of 75.77 chlorine 35 atoms and 24.23% chlorine 37 atoms. What is chlorine's atomic mass? So they gave us the percent abundances, right? And we need to turn these into fractional abundances. In order to do that, all you do is move the decimal place over 2 times. So that's what I did right here and right here. Now, in order for us to set this up, we have to take our abundances and then multiply it by the masses. So I set these up and I wrote out our fractional abundance times the mass of that isotope. Do not forget the units, please. Please get into the habit of always writing out the units that you need to have written out. As for fractional abundance, it doesn't have any units, so don't worry about that one. Now, I calculated out my answers, and you can see here that I have kept all the possible digits I can. So, following the rules of sig figs, first I multiplied. Both of these numbers in this multiplication had 4 sig figs, meaning that your answer coming from that multiplication will only have 4 significant digits. So we're going to underline those 4 right here. The same thing for this side. Okay, so keep that in mind, that those are actually the only 4 significant figures within that. So it was 4 sig figs here. I'm just writing this 4 sig figs, 4 sig figs. Okay, now when we add this up, we get 35.4546 AMU. So because both of the numbers that we added up, we're going to look at the sig figs that each of them had. This one, now we are looking at addition. So because of that, we are going to look at the one that has the least number of decimal places. The one with the least number of decimal places is actually right here. So that means that we can only have 2 decimal places here. The number after that last decimal place we want is 4, which is less than 5, meaning that we're not going to round up. So our final answer will be 35.45. Now, I want you to go to your periodic table and take a look at what the mass is, or you can go to the previous slide, and hopefully that'll all make sense now.